on this computer.
Thanks, Carmen. So we pick our subintervals, make this picture a little cleaner. We pick our x value, x1 star, we run him up to the function, form a rectangle. Pick an x2 star, run him up to the function, form a rectangle. x3 star, up to the function, form a rectangle. x4 star, up to the function, form a rectangle. Okay, then A, the area, is approximately equal to the sum. Again, we're thinking there are n of those, not 4. 1 to n. On each subinterval, I take my chosen value, xi star, plug it into the function. That's how tall the rectangles are. And then I multiply by delta x, which is the same it's always been, b minus a divided by b. And that seems like a reasonable way to estimate. I think I said this before. Like, if you never studied calculus in your life and you wanted to kind of estimate how much area is under the curve, that's probably what you do. Like, just fill it up with rectangles best you can. And we could be a little more exotic. We could make like trapezoids. We could make triangles across the top. But just kind of a common sense way to approximate the area. But we don't want to approximate it. We want it exactly. And we'll take care of that in just a minute. So this particular setup, a sum, a function at values spread across the interval a to b times delta x. That's a very important construct for us. In fact, it has a name. It's called a Riemann sum. Bernard Riemann was a German mathematician involved in the foundation of calculus, along with other names you've heard about, Isaac Newton, and so on. So there are kind of 3 ingredients of a Riemann sum. I wonder if this blue pen is any good. It absolutely has to have a delta x there. No delta x, no Riemann sum. It has to have values, the xi star, spread across the interval, roughly evenly. So that's the second thing. And of course, the third thing, because it's a sum, it needs to be a sum. Those 3 things together. On the exam that you took on Monday, one of the optional problems, I asked you to estimate the area. Remember that problem? And I was also asking you to find the value of a Riemann sum. Now, I didn't say it that way because we hadn't talked about them, but that's all a Riemann sum is. It's estimating the area according to what we've said today, using rectangles. Okay? And then, to get exactly the area, we need to let the number of rectangles increase without limit, while leaving the interval the same, a to b, so we're just going to take the limit as n goes to infinity of our Riemann sum. Okay. Now I'm going to show you we can actually do this. Find the area under y equals x squared plus 1 on the interval 0 to 3. Period. Use right-hand endpoints. For the xi star values. Okay. I want to show you we can actually evaluate them. Okay. I think I was referring to this, the area problem on the test, that I said on the video, you'll hear this again, like I'm surprised at how few people drew a graph. Like that's the first thing I would do, like 1 over x plus 1 or 1 over x minus 1. There were two versions of the exam. It's a hyperbola. We know what it is. And I think you just draw that graph and then you just plug your rectangles in. It would help so much. What's the famous saying? A picture is worth 1,000 words, and sometimes a picture like, man, it just shows us exactly what we need to do. All right. So this, I say, I'm going to draw a graph. X squared plus 1 is a parabola. We want to go from 0 to 3. It doesn't have to be super accurate, but in fact, I say on the video, it doesn't even be accurate at all. But if I draw the graph, I can see how to fit those rectangles underneath it and hopefully get their areas. So delta x we need, if we're going to evaluate this limit, I got to know delta x. Well, that's the length of the interval, 3 minus 0 divided by n. I need to know what xi star is because I'm going to plug it into the function. See? And then sum over all of these guys. So here's x1. Again, we're using right-hand endpoints. So x1 star is this guy clear over here at the right. That's x1. And how far is that away from 0? If I go from here to there, how far have I gone? Delta x. 3 over n. Right? So what's the next one? x2 star. How far do I have to go to get here? What's the x coordinate of that point right there? And the answer is 2 delta x's. Got to scoot all the way across the first subinterval and then all the way across the next one. I randomly said, let's use right-hand endpoints. I could have said left hand, I could have said midpoint, but I just chose. And as long as it's on the subinterval, perfectly fine. You know, over here, we don't really care. Xi star needs to be on each the appropriate subinterval, and the right-hand endpoints are. So I'll ask you, what's x3 star? 3 delta x's. Okay. To take advantage of the sigma structure and what we know about sigma, I need to write xi star. And what do you think it is, Eric? I times 3 over n. Right? x5 star is 5 delta x's. x12 star is 12 delta x's. Therefore, xi star is I delta x's. And now we're ready to do the calculation. All right. The first thing we're going to do is plug our xi star into the function. So here's what it looks like for all values of I, right? 1 all the way up to n. And the function says whatever you're plugging in, you got to square it. Let's square it. I times 3 over n squared. And then add one more. So this little guy right here is f of xi star. And then I have to have a delta x at the end. Well, delta x is 3 over. Okay, so that's what we need to evaluate. Any questions? So now we just let the things we know about sigmas, about limits take over, and we just see, like, what do we have to do to figure this thing out? Notice I can take this 3, I can pull it through a sigma, we know, and I can pull it constant through a limit. So let's take it all the way out. Okay. And we'll deal with it at the very end. We'll ignore it, and but we'll keep copying it down. But we'll deal with it in the very last step. Now, the variable of this sigma is I. It's I that goes from 1 to n. So this 1 over n is a constant as far as this sigma is concerned. It's not a constant on the limit because that's where n changes. So I can pull it through the sigma, but not through the limit. So we'll pull it right there. And then I have the summation I equals 1 to n. If I square that thing out, I'm going to write it like this: 9 over n squared, I squared, plus 1. Okay. Looks a little bit like a 4, but it's a 9. Okay, are you with me? Sigma of a sum is the sum of the sigmas. So let's use that. So notice, again, I is a variable. This 9 over n squared is a constant, and we know we can pop constants through a sigma. If I sum the number 1 n times, what do I get? Plus 1, n. You get n. 1 plus 1 plus 1, a total of n of them. Okay, questions? What should I do next? Anything suggest itself? Sorry, Harry. Do we know how to sum squares? That's what the first sigma says. Sum the squares. Do we know how to do it? Yes, we do, Julian. You're nodding, I think. Now, maybe, do you know, or do you just remember knowing? Yeah, what was one of our formulas? When we, remember I told you the story about Gauss summing the first 100 integers? Well, the very next theorem, the very next property I showed you was how to sum squares. And maybe you remember, I bet somebody does, but you're just too shy to say it out loud. So I have this 9 over n squared. And then when we sum squares, we get n times n plus 1 times 2n plus 1 divided by 6. How many of you had that written on your note cards on the exam? Yeah, probably all of you should have. It turns out you didn't need it, but you know, who knows? It appears to me that none of us really know that formula, so it should have been on your note card just in case. There are people that used it. I mean, the problem on sigma had is only summing the integers, not their squares. And so we didn't need this. So there were a few people that tried to fit it in somewhere.
Wait, what did you do there for that last step?
I summed these squares. And we learned a formula for summing squares when we first learned about sigma. It's this chunk right here. Okay? So now we just have a limit. Let's take our 3 times the limit as n goes to infinity. Let's push this 1 over n back inside. Okay? So it has to go in 2 places because of the sum. It has to impact this term and it has to impact that term. But when it goes to this term, notice I can just use it to cancel this n out right here. Okay, so let's do that. I get 9 over n squared. And this n cancels that, and then I have n plus 1 times 2n plus 1 divided by 6. And when this 1 over n gets distributed over there, what do I get? The beautiful one. All right, we're almost done. the limit of a sum, you have a question, Eric?
I was,
Looked like your hand was about halfway up and back
I
down.
was about to ask about the process, whether it would be a smart choice to then from here FOIL out the n plus 1 times 2n plus 1 and then make sure then we have an n squared, which we could then cross
Yeah.
out the other.
Yeah, so if we need to do that, we'll do it.
Okay.
Okay, I'll see if I can talk us through not having to do that, but if we need to, we can absolutely do it. The limit of a sum is what? If they both exist. Okay, and you can see I have a sum here. So we're gonna break it, we're gonna cross our fingers and hope both limits exist. What's the second one? 1, yeah. So no problem there. Now, the first one, I think Eric's kind of referring to it. It's a polynomial divided by a polynomial. Okay. Can you multiply it out in your head, like the 9 over n squared? So the 9 goes in the numerator, the n squared goes in the denominator. So we have a second degree polynomial divided by a second degree polynomial. Can you see that? I can write it right here. 9 times n plus 1 times 2n plus 1 divided by 6n squared. See that? So how do we get limits at infinity when I have a polynomial divided by a polynomial? If the degrees are the same, are they the same? Yes. So say it again, Carmen. The ratio of the leading coefficients. What now we have to, do we need to multiply it out or can we see in our heads? Like what's the coefficient of n squared in the numerator? If you imagine multiplying it out. Yeah, look at my little simplified guy here. What is it? 18. And what's in the denominator? 6. 3 times 4. 12 units of area. Got our answer.
What did you plug in?
And you would be right. So remember when we first learned about the derivative, it was the limit as, what did we call it? H. And you know, we found that fairly challenging to work with if the function was halfway complicated. And Carmen, we found a trick, right? We learned about power rules and product rules and quotient rules. And so maybe it's going to turn out the same way. In fact, if you think about it, the really crucial step here was that we knew how to sum squares. Okay. If the function would have been, instead of squaring, if it would have been the square root, have I shown you how to sum square roots? I haven't. Guess why I haven't? There's no way to do it. You'd just be stuck. So maybe there is a trick coming up. We'll see.
Excuse me, how did you get the
At least for simple functions, we can do this. Just right straight from the definition. Remember the picture I posted on the TV where I think they broke the area down into 32 rectangles and it looked super smooth, right? But we can let it go to infinity and actually do the work, at least for this function. Oh, you think Michael's talking to me?
yeah.
You're right.
Okay, so how did you go from the last step over there to getting whole numbers?
All right.
To the top left.
That is a second degree polynomial, and that is a second degree polynomial. The limit is at infinity. So we know it came in handy on the test. Well, not quite for you guys. Well, it did, just a different result. I'll show you what I mean in a minute. Second degree over second degree at infinity, the limit is the ratio of the leading coefficients. So now Eric said, should we multiply it all out? And if we need to, we absolutely should. But if we can find the leading coefficient without it, then I can see, if I get n squared, I'm going to need to take this 9 times 1, the coefficient there, times 2. That's going to be the coefficient of n squared. That's my 18. And then down below we have a 6. And then you just do the arithmetic.
Oh,
Okay? So, Carmen, this is the only one we're going to do this way, but you know, you can do it, at least for nice functions. But we are going to learn a trick, not today, but someday, soon. So I was referring to your limit problem on the test, and you may remember it was kind of weird. I don't even remember. I think I had 4x plus 1 in the denominator. Does that ring a bell? Cubed. Then I had something like x plus 15x squared. I don't know. But 4x doesn't really matter. That's what your problem looked like. The morning class, they had a cube right there. But somehow between printing the morning class out and giving it to them, going back, and I made just a few tweaks so all the answers are different, I lost my third power. So your answer was supposed to be the coefficient of x cubed. I think it was 2. I didn't write it here. Actually, it was 3 divided by 64. But your numerator is a quadratic because I made a mistake. So the limit is actually 0. It's not a third degree, it's a second degree. It still is a third degree on the bottom. So, you know, we still knew how to do it. It didn't ruin the problem. It just kind of changed it a little bit. And it made it easier for you guys, if that makes you feel any better. All right. Are there any questions? So let's take a look at this thing. Limit as x goes, or n goes to infinity of the sum f of xi star delta x. We know that if the function is non-negative, that limit is the area under the function. Right? When we take a look at the structure of it, again, this is a Riemann sum.
Muted.
The limit of a Riemann sum. Okay, this guy has a fancy name. He is the definite integral of the function f of x on the interval a to b. So that's his name, the definite integral. And we have a symbol. Like, it's fairly tedious to write that thing out. I mean, it'd be good for us. Maybe we would really become aware of what all the ingredients of a Riemann sum is. But we're going to introduce a symbol. Like, this is too messy. This is too many words, so we're going to introduce the very own symbol. It's going to have an elongated S sign with a dx. Have we seen that before? We have. The function that I want the area under, he goes in this slot. And then, you know, the thing that I haven't really shown yet is this interval. Well, I mean, the interval is crucial. If the one we just did, we went from 0 to 3 under x squared plus 1. Well, if I went from 3 to 6, would I get the same answer? No, there's way more area in there. So the interval matters. I have to show it. And the way we do it is by a subscript and a superscript on that elongated S. Okay? This is why it works. This is what we call it. This is how we symbolize it. So we get to write it this way instead of this way. And that's a super good advantage, especially since, notice, if you look at the limit of the sum, the values of A and B are disguised in there. I mean, they're part of delta x, right? But they don't really show up explicitly. And we want them to, because like I said, it matters if we're going from 0 to 3 or 3 to 6. We get different answers. So we want the endpoints to be totally obvious, and now they are. All right. So let's think about this. We have a brand new symbol, very much like a previous symbol. And this guy, when he exists, it's a limit. It may not exist. It equals a number. What we just figured out is the definite integral from 0 to 3 of x squared plus 1. What number is it equal to? 12 is what we got, isn't it? It took us a long time to figure that out, but we did it. And we did it right. On the other hand, the thing that looks almost like that, so this is a definite integral. This guy we defined earlier, what did we call him? We called him an antiderivative, but what other name did we give him? An indefinite integral. Yeah. And it's a totally different thing. It's equal to a function, not a number. And it's even more complicated than a function. It has any old constant. So very, very different things. Almost the same notation. So Carmen, the catch is we're going to discover that the indefinite integral will help us get the value of the definite integral. That's why the symbols are similar. Okay? But not today, we're not going to figure it out. But we will before the semester is over. Are there any questions? All right, so some technicalities. We define the definite integral as a limit, and we know sometimes limits exist, sometimes they don't. So let's talk about that for a second. If the integral from a to b, I'll write in parentheses, which is actually a limit, exists, then we say something like this. F of x is integrable. It has an integral on our interval, which is a to b. Okay, if the limit exists. Earlier in chapter 3, we said if the function has a derivative at a certain point, we said it's differentiable, right? So same concept here. The details are different, but the idea. Integrable function means this limit exists, and therefore there is a number associated with that symbol. And the good news here, we call it a theorem, I'm not going to prove it. If f of x is continuous on a closed interval, a to b, closed is important, then f of x is integrable. That limit has a value. Integrable. So we know the function x squared plus 1 is integrable on the interval 0 to 3. We found the number, 12. But that function would be integrable on any interval because it's continuous everywhere. An example of a non-integrable function, without justifying it, but I'll just tell you, f of x equals 1 over x. So I got to make something weird happen. Make it undefined at 0, is not integrable. You'll learn about this in Calc 2. on the interval, on any interval that contains 0. In fact, on this one, 0 to, I don't know, 2. Think about it. The function has a vertical asymptote, right? It's that hyperbola. We're going to go up to 2. So you can see the area is unbounded. It goes on forever, which in and of itself does not violate integrability. But this particular function, it does. Okay? You see the problem? Yeah. Now notice, that function is continuous on the open interval. But I'm saying it's not integrable. Okay, so it matters that we have a closed interval. Like I need the function to make it all the way to A, all the way to B. And if it's continuous, then absolutely it's integrable. Okay, if I take the interval from 1 to 2, I stay away from 0, the bad problem, then no problem, that's integrable. It's continuous on the interval 1 to 2, right? The only place it's not continuous is 0. If I can stay away from 0, no problem, the integral will exist. The limit will, therefore the function will be integrable. All right. Are there any questions? None. To be guaranteed. Okay, and it gets complicated, which means it gets fun. For example, you'll write this in your notes. This is like Calc 2 talking. 1 over x is not integrable. On the interval 0 to wherever, 1. But you see the problem over there, sort of. But guess what? 1 over the square root of x, which has the same problem, is integrable. And we don't really know the graph, but we know it's going to go to infinity as x goes to 0. So really, the graphs look the same. I mean, they're not, but as far as what I can really show on the whiteboard, they look the same. But there's something different about 1 over the square root of x. The limit that defines the integral exists for 1 over the square root of x, but not for 1 over. So it's complicated, which means, you know, it's super fun. Things are not trivial, so you really get to dig in and think deep and hard, and that's what we love to do. Right? Of course, right. Any question? Okay, let's talk a little bit about area. So right now we're saying, like, if x is non-negative on AB, then I'll write using our brand new symbol, a to b f of x dx equals the area. Assuming it exists, and we'll assume it, between its graph and the x-axis. Okay? We all fully believe that, right? I mean, that's been our whole motivating reasoning leading us to this thing called the definite integral. Okay, what I want to do is, how do we think about it if the function is not non-negative, like if it becomes negative? So we'll do it in stages. First, we'll go to the opposite extreme. The function is non-positive, less than or equal to 0, everywhere on our closed interval, a to b. Then the integral, oh my sisters, equals the negative of the area. I'll write a minus sign, and then I'll say the area between f of x, actually its graph, and the x-axis. So we'll think about areas as being positive things. But if the function is non-positive, negative, if we can find a number represented by the definite integral, it's going to be a negative number. Right? How can we tell it? Remember the definition. The integral from a to b f of x dx is the limit. You don't need to write this in your notes. It's already in there some. I just want to look at it while we talk. F of xi star delta x. Now, delta x is always positive. B minus a over n. B is bigger than a. So it's always positive. If the function is negative, then f of xi star is going to be a negative number for every value I pick, right? I have no choice. If the function is always negative, then at every x value I choose, I get a negative number. So a negative times a positive, what time is that? That's a negative number. So you don't want to tell me. That's okay. I'll answer my own questions. If you add up a bunch of negative numbers, what kind of number do you get? Yeah, if you take a limit of a function that is always, always negative, what kind of number do you get? Negative. So if this is true, and this integral exists, it's going to be a negative number. So how do I think of that in terms of area? Well, it's simple. We'll just think of area as a positive thing. And for example, if there are 5 units of area below the x-axis, then the value of the integral is going to be minus 5. We'll just attach the minus sign because all of these guys are negative. It forces a negative answer for our definite integral. Let me see if I can do this. What time is it? 5 minutes. Find the value. The integral from 0 to 3 minus x squared plus 1 dx. Okay. Except for the minus sign, this is exactly the integral we found the value of before, right? And when you multiply that function by minus 1, instead of being a parabola up here, it's going to be a parabola down here. So the area between the axis and the graph, it's the same amount of area, but now with the minus built on there, they're all negative. So the value of this integral is negative 12. So I know because we solved that problem, we got 12. And now if I make the function everywhere negative, it's just going to change the sign. So it tells me there are 12 units of area below the x-axis. The minus sign means below. Okay? Finally, so to start with, just to make life easy for us, you might need to write that in your notes and underline it 3 times. We assumed the function was positive. Found a way to calculate the area. And we actually did it for one function. And then we go to the opposite extreme. We assume it's negative and we see how we're going to interpret it. Okay? And we can relate it back to the one we did do to find the value of an integral. Now, for any old function whatsoever, positive, negative, whatever, for any f of x, we're going to think of the integral from a to b f of x dx to be equal to the area, assuming the integral exists, above the x-axis on the interval a to b minus the area below. I won't repeat where we're looking, it's the same, below the x-axis on the interval a to b. And there's a fancy name for that. It's called the net area. And just in case it's not clear, let me show you. let's say we have a function whose graph looks like this. And we're going to go from A to B. And somehow I know there are 6 units of area here and 4 units. Let me grab a point right where it crosses from positive territory into negative. All right, based on what I've said to you, the integral from A to B, this function is f of x. What's the value of that integral?
2.
Pardon?
2.
Oh, you're right. But that's not the question I wanted to ask. It's a good answer. From A to C, what's the value of that integral?
6.
6. And from C to B, pardon?
-4.
-4. It's below the axis. There are 4 units of area. And then, Eric, if I go from A all the way, skip over C, what do we get?
We get 2.
Yeah, the net area above minus the area below. If the value of an integral is negative, it means there is more area below the x-axis than there was above it. Now, it could be all the area below it. It depends on the function. Any questions? So unfortunately, Carmen, we didn't get to the quickly. We may not even get there on Monday, but we will by Wednesday. Any last questions? All right. Have a wonderful weekend. We'll see you Monday. Thanks for checking in, Michael.
Welcome, sir. So will there be a recording of this, like posted onto the
Yes.
class? Okay.